Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, thanks for coming. It's my great pleasure to introduce Adam Smith, who is currently finishing his postdoc appointment at University of Washington in the Center for Game Science, working with Zoran Popovic. So before this, Adam was a PhD student at UC Santa Cruz, where he worked on HCI, AI, game design. And Adam has kind of continued his interests at UW as well, where now he is working on applying more formal reasoning tools, automated reasoning tools, constraint solving to the problem of game design. And he's going to tell us more about it today.
Yeah.
Over to you.
Thanks, Sumit. Okay, let me put this back up here. This talk is going to be about some formal methods applied to sort of creative design tests. So let's start by looking at a few what I mean by creative design tests. So suppose on the very non-formal end that you're an artist, maybe like a film composer. Your job today is to lay out an important melody. You're deciding where to put the notes on the staff under certain rules of harmony and form, and making things repeat but not too often and so on. You've got a personal style that you want to make sure comes through, but you also have audience expectations, so there's external constraints. On a more technical end, you could be someone designing a CPU. This is a very super simplified one. Here you might have a formal specification for what it should do, but it's your job to figure out the low-level design of things that implements that high-level specification. And you're considering things like cost and timing and propagation delay and lots of technical properties like that. Another thing you might do as a designer is you could be designing levels for a game. This happens to be from the level editor for Portal 2. You're trying to make sure that when the player starts in one place, they make it to the exit, encountering the content you want them to see while not encountering the things you don't want them to see. It should somehow be obvious which way to go, but there should still be some challenge. So there's sort of formal technical challenges here, but as well as aesthetic ones. So in each of these three cases, whether it's the music, the digital logic, or the level design thing, you're a designer who could benefit from some kind of automation in your job, some tools to help you search in the space of alternative designs. So this talk is about mechanizing design, not automating design in the sense of like fully replacing designers. This is to make the individual designers more powerful, move them up the layers of abstraction. So to start, I'm going to claim that inside of every design task, inside of every design problem is a search task. It's not like your job as a designer is to search, but it's one of the things that you repeatedly do day after day. You're trying to search through the configurations, arrangements, and notes on the staff as a musician, define and instantiate modules in the digital logic case, or lay out and populate these virtual worlds in the game thing. Each one of these design tasks is formalizable in the sense that if you spent your whole career, you could write down all the constraints you think are of use there. But really, you might want to just write down the most interesting constraints, have the computer help you with those, and then use your own personal creativity for the rest. It's been a while since I gave this version of the talk, so I have to remember what I was doing. Oh yeah, okay. So despite your ability to formalize these various design tasks, you got to keep in mind that the requirements on your particular task for that day are always changing based on the rest of your team, the expectations of the audience, and so on. And also because of this thing called ill-definedness, which sounds like a sort of ill-defined word, but it's a big idea in design studies. This influential document gave me this quote that I like. Design is a type of problem solving in which the problem solver views the problem or acts as though there's some ill-definedness in the goals, the initial conditions, or allowable transformations. So it's not the designer's job to give you exactly what you asked for. It's their job to sort of come up with the rest of the specification of what you really wanted, and part of the way they do that is by offering potential solutions along the way. This is sort of the idea that the quote attributed to Henry Ford regarding the invention of the mass-produced automobile. If he had asked people what they'd wanted, they would have said faster horses, but instead, of course, he gave them the automobile. So that was like some excellent design thinking, sort of going with this mindset of ill-definedness. Even if people ask you for something, you might want to give them something else that they actually want more. So this the search task that comes up is computationally complex. Sometimes people, when they're making things that generate music automatically, whether they're composition assistance tools or just purely generative music things, they might phrase it as a constraint solving task, which you might feed, say, to a sat solver or something. So you might think of this as not that music composition has complexity NP-complete, but it's around that's sort of a comfortable way of formalizing the formalizable aspects of it. If you have a high-level behavioral specification for what you want your, say, CPU design to do, and you want to say, well, can I just have the computer solve for the arrangement of pieces that, for all inputs, agrees with a high-level spec? You might call this circuit synthesis, and this is one of these classic sigma 2p complete, which is the next layer above NP on the polynomial hierarchy. Likewise, if you're working in a game design domain, depending on whether it's a multiplayer adversarial game or not, it could reduce to one of these simpler things, or it could be much, much worse. But maybe you think this is sort of like just something that only happens in the abstract. This doesn't apply to the common case. Well, there are popular games like Minecraft with mechanics rich enough to express sort of general purpose computation. So this is somebody's, I believe this is like their 8-bit ALU that they have for a larger, complete working processor design in Minecraft. But maybe say like players don't actually have to build working computers in the game. This is just what some hobbyist made. The game doesn't force you to build working processors. Well, there are other games, particularly ones about, say, teaching you programming, or other ones that sort of have the same type of puzzles but skinned in a different way, that legitimately are about programming, building state machines, and so on. And like, it's not just that this is a hobbyist activity. This is what the game really asks you to do. So when you're designing puzzles for this, you're thinking over all ways people could build a program that satisfies the constraints you've set up. And it's not just simple state machines. In a game like Space Chem, you're dealing with like asynchronous communicating processes and buffers and flows and so on. It gets really interesting. Like, games aren't actually, once you strip away the surface graphics, aren't very different from a lot of the things you would apply formal methods in software engineering to, or even electronic design automation and so on. So the usual response to this in the game industry is to just throw a lot more human designers and QA testers at the project, where you have someone make a level, and then you have a bunch of lesser paid testers go around and try to break the game in various ways, write down their notes. And this is expensive because you have to pay all their salaries, but it's also sort of unsatisfying from a design perspective because for complex designs, no matter how many people you throw at it, there's still going to be some edge cases that they never checked. Likewise, because it is expensive, this is not helping you sort of access new areas of a design space that you wouldn't otherwise. You're just paying a lot to have high assurance about the thing that you made. This is sort of the usual motivation for all software verification stuff too. But I'm sort of specializing it to games here. And as we apply this type of stuff to not just games for entertainment, but for education, for science, for health, this long tail of things, it becomes more and more worth it to invest in automation that is relevant to these things, because they do touch a lot of areas of society now. So basically, what I do is I sort of invest my time and attention into building design automation tools that work primarily in games, but also give us a new perspective on what we can do in other domains. So I'm saying we should mechanize design, not automate it, but make these tools that assist you based on this idea that computers are pretty good at search and checking all these alternatives. And one of the things that this can give us is design assurance. They can catch costly mistakes early, the usual verification thing. For little micro design tasks like how do you arrange the blocks in a little maze so that someone has to spend 8 steps to get out of it, well, we can synthesize an arrangement of that. You don't need to make and check something yourself every single time under the idea of synthesis here. And also, if these tools give you really fast feedback, you can explore more ambitious ideas and know that you can see directly through to their edge cases. You can also ask the computer for, within some representation, to search the space of things that might solve that design problem, and occasionally get solutions that you wouldn't have thought of yourself. And then you say, well, I like that. I want to run with that, and look at other variations on that. So that, yeah, they can show new solutions. They can maybe even prompt reformulations of the problem. Maybe like if your design task was to make some awning to cover the balcony. Maybe you see a strange glitchy solution. You're like, well, maybe it's not just about covering the awning. It's about making it feel a certain way when you're out there. If I have to boil down what I do into one sentence, and I will cheat with a semicolon, so it's sort of two, it's this idea here. The designer sketches a space of appropriate artifacts using a constraint program, and I'll tell you about the technology I use for that later. The machine samples an artifact from this space, and upon examining the artifact, the designer refines the sketch. So it's not that it does the whole job for you, but it does what you told it. You realize that's not what you wanted, and you iterate, and that's the flow. So overall, what I'm doing in this talk is telling you about how I model design spaces in a constraint programming language called AnswerSet programming, which, how many of you have ever heard of it before? 1.5 and a 0.25, whatever. Okay, I'll go into more detail later. But you don't need to have previously seen it in order to make sense of this. You can actually replace a lot of other technologies in there and still get the same results. I'm going to show you 3 projects that are all tied to a particular game, just to keep things compact and coherent. Then tell you a little bit about what other people are doing with it and where I want to go next. So modeling design spaces. Don't worry about AnswerSet programming yet. I just want to talk about what design spaces are in my vocabulary. So what is in a design space are different artifacts. These are things you could construct. If you're thinking about the design space of futuristic chairs, you might have a representation of these artifacts in terms of parameters describing the lengths of edges, the joints and radiuses of curves, and so on. And in that representation, there are lots and lots of alternatives. Maybe there are ones that, if I can point again, they're upside down, they're different colors, they're stretched, they're wide, they're rotated a different way. So these are sort of like all possible things you can come up with in that representation. What I call a design space is sort of the set of artifacts that the designer thinks are applicable for a particular design task. Just because you can represent an upside-down chair doesn't mean that the chair is automatically appropriate for the specifications you've gotten today. So the design space is, in a fuzzy sense that is only ever in your head, the set of artifacts that you think is appropriate. And if all the artifacts could be described by a small number of continuous degrees of freedom, you could literally write down some like linear constraints and say like, oh, here's the polytope of valid chairs. But of course, things are not that simple. This is just my sort of visual metaphor for a representation of the design space. So if you put in a new chair, for example, this design of an extra tall one, you can say, well, is this inside or outside the design space? Which constraint is rejecting it if it's not? Or maybe project it to its closest valid thing and show me that one. Or you can say, well, there's a lot of volume in this space that I haven't checked myself because I've only looked at 6 chairs so far. Show me some other things in that space. And I'll pass judgment on those and say like, oh, that one's interesting, but it's not a chair at all. By sampling things that are in the volume of here, you get prompted to add and remove and refactor your existing constraints. And of course, I said like this idea of having, like this picture has like 3 continuous degrees of freedom. It's not that simple. In order to express really interesting and applied design spaces for the projects I have coming up, you got to use a much more interesting constraint modeling paradigm than just linear constraints. And what I use is this thing called AnswerSet programming. And I'll spare you the history of AnswerSet programming coming from the AI literature and knowledge representation. It's basically a declarative programming language for defining a space of solutions. And we're going to apply it to modeling the space of valid artifacts or appropriate. To make this really concrete, hopefully you've all seen the graph coloring problem before. Yeah. So you could think of sort of a generate and test process where we're going to generate all possible colorings, and then we're going to test whether we accidentally colored 2 adjacent nodes the same color and reject them otherwise. And perhaps we might want to minimize the number of colors. So this is sort of a specification for the problem, and I'll show you how to translate this into a few lines of AnswerProlog, the language of AnswerSet programming. And so those guess, deduce, forbid things translated almost one-to-one into rules here. And I'll tell you about the details in a second. Interesting problems usually break down into the similar guess, deduce, forbid paradigm, but there might be like 100 lines in each one or something like that. Usually these things don't ever get very big, but just so that this strange language makes sense to you, just talking about the first thing here, this is sort of saying, If n is a node, it implies that the set of colors that are assigned to it has cardinality or size 1. So you can think of this as like an actual logical implication arrow, and this is sort of quantified over all nodes n in our graph. This is not giving you a recipe for which colors to assign. It just says what makes a valid assignment in terms of things having exactly one color. From that particular assignment, represented with the assigned predicate, we can sort of project out or extract the set of colors used across the whole graph, which we'll later down here use to define optimization metrics, say minimize the count of those colors. Likewise, if you write a rule here that has no head to it, this is how you forbid configurations. So if we ever find an edge between nodes n1 and n2 such that they're assigned the same color, well, then this is an invalid assignment and it should be thrown out. And of course, this program doesn't run top to bottom. These get translated into something. Historically, they did get translated directly into the input for a SAT solver. These days, there are specialized AnswerSet solvers that are less indirect than that. But the similar idea of translate it into a constraint program, and then someone else's algorithm that they've spent decades working on solves it more efficiently than I ever would. Yeah, I'll skip over those things. Did I say enough about this, or are you curious more about the code, or? I'll go on. OK, right. So the very last little bit of that is that these solvers are very much like SAT or SMP solvers. So when I model, say, a program synthesis problem in this paradigm using basically the same technology that say, Sumit might use for program synthesis and so on. Yeah, and instead of reasoning about the colorings of graphs, we're going to reason about the design configuration of artifacts. So let's see this in some concrete applications. These projects I'm using it for are all part of, tied into a, yeah, they're all tied into this game called Refraction. And I'll give you a little taste of the mechanics so that you know what the examples later mean. So this is a game about teaching, the intent is to teach kids fractions. We don't know whether it actually does that or not, but it's definitely a game that involves fractions. The idea is that you start with a board blank like this. There's a laser with power beam, or with beam power 1 coming out, and you can use pieces like these to split and combine. This is like dividing and adding fractions. You have to keep track of denominators and so on. But there's also spatial challenges like trying to collect secondary objectives, or the beam can't go through these fixed asteroids. And one of the other twists is that you're not allowed to rotate the pieces. So sometimes you'll make the right power, but you'll have to find another way to construct that same fraction from another direction. So there's lots of cool traps you can set for the player. So when you're playing this, you're picking up pieces from what we call the tray over there to build a network out here. You can also think of this as a little data flow program if you like, but spatially embedded. And your goal is to prepare the fractions wanted by each of these little spaceships with cute animals you got to save. And this particular game, which was made before I joined University of Washington, it's been deployed online, it's been deployed in classrooms, it's got a bunch of awards as an educational game, millions of players, so it's a very significant project, and we want to make this game better and better over the years, and this has been my target for a lot of automation research. When you're playing through this game, or at least the original version of it, you work your way through these various worlds. Each one has maybe 8 levels in it. There were different versions with different numbers of levels, but everyone plays the same levels in the same order based on what our level designer, who happened to just be an undergrad, just making levels as to, to get credit or research experience. So it's not the most informed level progression, but it's the one we went with. Really, we'd want to have like the right levels for the right student at the right time. If you seem to know something, maybe we can jump you onto levels that involve different concepts. Or maybe we can give control of these generated levels to a teacher, so they can say, well, I want every kid in my class to play Refraction today. I want them all to be doing 2 layers of division, but only things involving prime factors up to 3 or something like that. But they don't need to design the levels. They just need to give us these high-level specifications. So the first project I'm going to talk about, generating customized levels. And yeah, as I said, if we sufficiently abstracted this, we can imagine giving control over this to the teachers in the classrooms. Although it actually turns out the teachers don't really know what they want the game to do any day, so that didn't work out as we thought. But I'll still tell you about the technical end of it, because it embodies a lot of the other stuff I've been doing. So one of the things we wanted to do was take one of our pre-existing levels from the original game, which we know works to whatever degree it works, and we want to make lots of variations on those levels without having any manual intervention. So for a simple level like this, we might, this problem of graph transfer is extracting the graph from here. Extracting the graph is not at all hard. You just parse the data structure. And then we're going to solve for different embeddings or layouts of that graph in a new level so that when different kids are playing, everyone's, say, 4th level into the game would involve the same sort of mathematical graph, but their layout is different. You can't just recreate the spatial configuration you see on your friend's computer. You have to talk to them about, like, well, how did you make a half? Well, I used the splitter and the adder and so on. Or they use the splitter into the adder, into the bender, and so on, as opposed to saying, well, you put it in the top left corner, which has nothing to do with fractions. So the way we formulate this in AnswerSet programming, also this is a much more realistic level from the game, involving like the graph has like 16 edges, 47 nodes, which what's sort of nice is that the scale of this problem is fixed. It's not, we don't care to scale to graphs with 10,000 nodes. Like, kids are playing it on a 10 by 10 grid, so we need to handle that scale, but we never need to handle beyond that. So before I joined University of Washington, a couple grad students and some of the game development staff were starting to make a tool that could do this graph transfer thing. So they had this graph, and they're trying to produce one of these as outputs. So they had like a little randomized depth first search thing that would take any node that was not yet embedded, put it in a random location, and then for all outbound things, place pieces a random distance along that beam. And if you get to a dead end, you backtrack or start over with different random seeds and so on. And for little problems like this one, we could solve those, instantly. It could give you lots of different embeddings. It wouldn't really tell you if it got all of them, but it worked. But when they tried to apply it to real levels from the game like this, depending on your random seed, you might get it in 5 minutes. Sometimes it runs for 2 hours with no response. It was like really unreliable, and they'd been spending a couple months on this already, and it was getting to the point where they either need to scrap this and just go with handmade levels forever, or think of something better. There were also other complications, like they didn't support all of the original pieces and so on, which they would definitely need to do. So when I joined, I thought, well, this is similar to the design automation stuff I've been doing in the past. Let me see if I can model this in AnswerSet programming, where I'm not going to write an embedding procedure. I'm just going to write down the rules of a valid embedding. So in terms of that vocabulary of guess, deduce, and forbid, for every piece in the abstract graph, the non-spatial one, we need to give it an x and y coordinate. We need to decide for each little piece whether its output ports point north, south, east, west, and so on, because that's part of the puzzle configuration. And from that information, we're going to decide the relative configurations. Like, if two things have the same x coordinate and one has a y more than the other one, it must be north of the other one. From the relative positions, we're going to figure out whether there are free paths, if there's anything obstructing it. We'll figure out, basically do the laser flow simulation on top of that, and a couple of other things like that. And we're going to have constraints that say two pieces can't have the same x and the same y at the same time. We'll say there better never be an edge that occurs in the mission graph that we extracted from previous level that doesn't reoccur in the embedding, and a couple more things like that. And so to write this down in something that was 100% equivalent to the model in the game was 75 lines of code. And it took about 1 day to make the sort of proof of concept and another day of testing to make sure it was exactly equivalent to the one in the game. So compared to months of grinding and guessing random seeds and trying to parallelize stuff, this was just sort of write down what you want and you're done. So this felt really good. And it also gave us a lot of flexibility to add more constraints, which is important for this next step. So a random solution to that re-embedding problem might look like this. This is also a totally legal and valid thing. All the pieces are scrunched up on the left. All these pieces, for no good reason, are in a row. According to all the rules that I told it, this one is valid. And with some random seeds, we would get a thing like this. So when we started getting results like that, we realized that we have additional constraints, so sort of aesthetic constraints. Now we can get outputs like this one, where there's like spacing between everything. The blockers are arranged symmetrically and so on. Or we can decide whether we want symmetry, balance, and spacing on a level-by-level basis, just by making a little detector for whether things are next to each other and saying, if it has that property, it's not spaced properly, and so on, and reject it. Yeah, we started getting into the more aesthetic modeling after we got all the gameplay stuff done. And transfer of graphs from one level to the other was just one of the many tools that we needed for refraction. So instead of making a separate little AnswerSet program for each one, which we did for a while, And they were all small, pretty self-contained, but they were expressing essentially the same ideas of like the game mechanics plus other constraints. We sort of unified all those into one thing, which was it was twice as big as any individual one, so it replaced a lot of other ones. We just sort of wrote down the rules of the space of valid puzzle and solution pairs, sort of all configurations of pieces that formed a solution under any constraints that we put in. So if we put a constraint on what the mission should be, or put a constraint on which mathematical sub-expressions are made, depending on what we put in as constraints, we can use this one constraint program to make new mission graphs, new embeddings of existing ones. We can have it search for alternative solutions that do or don't practice other concepts for a fixed puzzle. We can analyze partial solutions so that when you're partway through solving a puzzle, we can say, are you sort of on the path to a solution, or is there some piece that you have to pick up in order to make progress? And we can detect that on a move-by-move basis. And we can also play around with variations on the game mechanics, because we don't need to make graphics for things to try them out here. We can add a new piece and see how it affects puzzle design, sort of in the abstract. So as a result of this, the refraction team no longer writes search algorithms. They just design games and write down definitions of those game rules again. So this next project deals with sort of coming to grips with the actual interactive nature of game design, which was overlooked. Yeah?
Did you also measure that the difficulty of instances in the same level were indeed the same as viewed from the observer's perspective?
Did not measure that. Or rather, if we had, it would have been sort of things like this, where I'm sure these levels have very different difficulties, even though they technically have exactly the same graph. So we had no expectation that transferring the graph meant transferring difficulty. We did know that it meant transferring mathematical expressions. But it was basically, from the experience of this, we knew that there was so much variation that we had not modeled at all yet, that we weren't interested in evaluating whether it transferred the difficulty or not. To this day, we still don't know what to do about difficulty. It's an extremely subtle thing. There are certain proxies for it, like just how many pieces, or does it use numbers you're not familiar with yet? And I think to really evaluate that, we need some like actual player models to go with this, which I'll mention a little bit later. But at least at this stage, we knew we didn't have a handle on the thing that would tell us anything about difficulty.
So what is wrong with this following naive suggestion to measure this? So you just have, do the A/B testing, right? You have two different crowds of people. You give them two different instances of the same level, and you see the statistics of how they perform.
That would tell us about that one other instance or that one alternative progression. Whereas, like, if we went from this thing, the output might look like this or it might look like that, and those will have very different things. So if we did an A/B test, it might say that this one is easier than this one, but that is not reflecting on how we generated it at all. Like basically, A/B testing can only tell us about the instances and not the system behind them. I mean, we could have done that study. I really just didn't want to do it because I knew it would only tell us about the effects of whatever random seed we started the solver with that day. Or at least until we started modeling these things later. And I'll talk about, that's going to come up a little bit later. So I want to go on from that. Right, so we have this sort of model of the game, and then we just have queries against the model to make a lot of our design tools. So this next project deals with sort of a major oversight we had in the previous formulation of the problem. Previously, we were really happy to get levels like this, like, oh, it's got symmetry and balance and spacing. It involves splitting the laser and recombining it. Oh, kids will learn that if you split something into equal parts and combine them, you get the whole back. Well, it's not actually that simple. If you give this puzzle to kids, they might find this other solution where you don't split, you don't combine, there's no spacing, there's no symmetry. All of the beautiful properties of our one reference solution turned out just to be the sort of wishful thinking mode. And controlling whether there exists alternative solutions with certain other properties involves changing the formulation property in a way that totally changes the complexity of the problem. And to make this more concrete and a bit more general, I'm going to introduce you two characters you can think of as working together on a game design team. The first is Elise. She's going to solve sort of problems that are quantified with an existential quantifier. Her goal is to design a level that is capable of supporting the required gameplay. This could be, you can tell Elise, please make me a level where someone splits the laser and combines it. Or basically, her job might be to make this one on the left, or the intent of that one. And her design partner here is Fiona, who's going to solve problems with a for-all quantifier. And she's the quality assurance tester. Given a particular puzzle, she's going to actually check whether all solutions really do check that property. So given these two characters, we'll sort of formulate the problem logically. So the basic puzzle generation problem, or the setup used in a lot of procedural content generation stuff in games, is given some predicate that we'll call style, could be any property you can check in polynomial time, show that there exists some puzzle P such that this predicate is true of that thing, whether it could be balance spacing, it could be that it did or did not involve the sub-expression of the mathematical sub-expression, did it come from a grammar or something like that. And because this problem exists something such that some polynomial time checkable property, you can hand this off to a SAT solver and sort of replace or mechanize Elise's efforts with a solver of that complexity. You can also say, well, for a given puzzle, we can tell her to act as a player. Find a reference solution to this puzzle, not shown the solution beforehand, such that the reference solution solves the puzzle and it demonstrates the concept on that particular puzzle. And again, it's not important that they're called solves and concept. They could just be any polynomial time checkable properties. For us, it was sort of like, when you simulate the mechanics, does this little subgraph of the laser graph exist? You can also combine these to say, well, just invent a puzzle out of the blue where someone can practice this. This is how we formulated it in the past. So we can say now, invent the puzzle and its a reference solution. That's basically the tools we had before. So even though this involves making a bigger thing, not just the puzzle, but its solution at the same time, it's still a problem of the same class. It's still in NP. Where things get interesting is when you want to involve Fiona to check the lack of, say, these shortcut properties that leave out the concepts you don't want. We want to tell her, given a particular puzzle, probably the one that Elise just made, prove that there does not exist an alternate thing that solves it but doesn't demonstrate whatever concept we're trying to show. And if you rearrange the quantifiers a bit, you can express this as for all. Basically, we want to say, given a puzzle, prove that solving the puzzle implies practicing the concept. This is what we really want for our educational games, and we didn't have the insight to formulate it in this way until we'd basically made all these tools that formulate it the wrong way. And really, we want to put these together. We could make one program that models Elise and another one that models Fiona and have like a generate and test pipeline, and then we'd actually have to make the two separate things. Really, we can just write down what the team should do together and hand that off to a solver that can handle problems of this complexity. So we want to say, there exists a puzzle and the reference solution that we're actually going to look at with a guarantee that for all of these other solutions, the reference solution is valid, like it's a good reference solution, and anything else that also solves it practices the concept. This is basically showing us that our reference solution is representative of whether the concept was demonstrated or not. And anytime you see a problem where you have exists some variables such that for all some other variables and then some quantifier-free garbage there, this is like the 2QBF problem. This is sort of like it's one of the canonical problems for Sigma 2P complete. If you want to think of it this way, it's the extra difficulty of solving something in NP compared to just some polynomial time algorithm, if they indeed are different. That same gap, do that again to figure out how complex this thing is. So it's a very complex problem from a complexity theory perspective, but in practice, we implement it for our new game. We still get solutions in under a second. It's very responsive. And this comes from the idea that because our design problem is attached to a real human context, the scale is sort of fixed to what is relevant to those humans. We know we're only dealing with the 10 by 10 world, and we never have to change that. So this is an example of one of the outputs that was generated from this new formulation. And the concept was that every target ship draws power from every source. This sort of means that you can't solve any piece of the puzzle in isolation. You can't just like route this source of power 1 to that thing of power 1 and then work on the rest. There are thousands upon thousands of ways of solving this particular level, but none of them escape this property that there's one entangled network. And if I gave this puzzle to you to solve, like I put down the fixed pieces and let you drag in the rest, you'd probably spend half an hour finding the one solution. Can you imagine if your job was to be the QA tester and promise your boss that, oh yeah, I checked all the solutions and they all require this property? Like, was that hard to find one, you have no assurance that that this property holds for the rest, other than that you tried hard. Whereas we just hand it off to a theorem prover, and it gives us that assurance. In order to express this in AnswerSet programming, which technically can express things at this level of complexity, it's just insanely difficult, and all the manuals, even targeting AI researchers, say, don't use these features unless you absolutely need them. So I basically made 2 new language constructs that you use when you're writing in AnswerSet programming in order to make these actually usable by people who are not AI researchers. They were named with reference to this design task. So if people know how to cast their problem in the same formulation with Elise and Fiona, then they can use these language features to express what they want with minimal additions to the language. Basically, I've got a little program translator that you write the program with my language extensions, and I transform it into one that has the right semantics. Then we feed that off to the solver. Oh, and because this has made formulating this type of problem easier, I've actually run into people who are using this library, which supposedly I made for designers to use. There are AI researchers using it in their multi-robot pathfinding stuff, just because it's a convenient way to express universal quantification in AnswerSet programming, finally. That's just a weird twist. So the last project looks at putting all these things together and putting sort of a human interface on top of that. And it definitely builds on this idea of the concept that we want to require at each time. So in a puzzle game or many other games, there's this thing called level progression, the set of challenges you go from one to the next throughout the game. And when you're designing these, it's really important to keep track of which concept you introduced when. If something is really difficult, you might want to delay it until the end, until people have mastered the prerequisites for it earlier. So keeping track of which concepts are introduced is really important even when you're designing these things by hand, which is basically the only way people ever make level progressions now, until now. So this is a zoomed-in corner of a really cool diagram that me and the other researchers found about 2 years ago. This is a diagram of the level progression for the game Portal 2. And the way you read this is sort of, this axis describes which mechanics. So this says grabbing, using portals, using the weighted storage cube, switches, panels, and so on. And across the right is time, sort of which level you encounter these things. So now I'm going to zoom out so you can see the whole thing. And on a nicer projector. Like when we saw this, we're like, oh, we wish we had this for our own thing, because at a glance you can say, well, on level 11 it uses, I can't even read these things because they're too dark, but on a good screen you can say like, oh, it definitely uses these concepts. It's continuing to use this one that was introduced previously. The little yellow spots are the first time that thing is used, so you know that level 11 better provide the tutorial explanation for, or at least the guidance to have them figure out whatever the new idea is. Or you can sort of slice it another way to say, like, for the switches mechanic, these switches that can open doors and so on, where are they used? Are they used only at the beginning? Did we forget to bring them back in the end of the game? So certain things like this diagram makes it clear that whatever these concepts are sort of just got dropped for like 10 levels in a row and then got brought in a little bit at the end, and there are some that are basically used once and a few other times. So like there's a really broad perspective you get from a diagram like this that we wish we had for our own game. We probably wish other developers had for their own games. This chart was not made by the developers of the game. This was made by a fan of the game about a year after the game came out. So though designers did not have access to this visualization, they probably had scribbled whiteboard notes that were out of date and so on, because requirements are constantly changing. But we wanted this for our own game, but we don't actually know who made it, or we don't know what country he's in to have him make it for our own game. So we would have to make it by hand. And better than that, we'd like it so that whenever we hand touched any of the levels, that maybe a little thing would pop up here to say like, oh, you've modified it. And also maybe we'd like to be able to take one of these bars here and just drag it over and have it sort of redesign the levels underneath to make that level. So that this was sort of our design fiction. Like we wish we had a tool that could do that. And well, if we had such a thing, it would be an instance of what's called mixed initiative design. The idea is that you want to combine human touch, direct manipulation of visual notation on the screen, as well as the ability to touch all the little details of a design with the inspiration assurance you get from a machine via synthesis and our automatic playtesting based on the tools I already told you about. So we wanted to make this intelligent user interface that sort of, previously to use all of our design tools, you'd be adding constraints to a file and running command line tools. We just wanted to make it tangible so that, again, our level design undergrad could have some better tools. So I'll show you some of the visual notation from this tool. These are screenshots of the real thing. So this is a little widget that describes the partial order concepts. A little blue thing here says that, I think this says that adding must be introduced after splitting, that splitting must be introduced after bending, and so on. So this sort of, across all possible progressions, this is sort of sculpting the space of progressions. And there's also pacing things like, we have many different curve editors here, and you put in your design intent in blue, and then it visualizes the current state of the design relative to that target there and shows you where you're furthest off from it. The next step is the progression plan. This is like, from these sort of high-level sculpting of a progression, this is a plan. This is not the actual set of levels. This is just sort of your sketch of which concepts will be involved in which level. And we borrowed that same notation of the little yellow as the first time things are introduced. So as before, like a column here says that level 20 is going to involve splitting, bending, blockers, and this will be the first one that introduces the wasted lasers concept. And of course, these are exactly the inputs that we feed into our level generator. And at the last step, each one of these vertical slices here corresponds to an actual concrete level design. So that's, when you're using this tool that we made, you're sort of jumping between all these scales at once. And I'll show you a little video of this in action. I think this video just shows using some of these high-level sculpting things, like changing the total concepts used over time and having it sort of rearrange this for you. Until we've looked at the details, they're all free to be changed by the tool. Not shown in this video is you can press the little L, which is supposed to be a lock icon, to lock these things in once you like them and have it optimize the rest to fit the other stuff. So it's not like this is your only control. Early on in the project, we were hoping that, oh, we could sculpt the whole game using just these beautiful curves here. It's like, no, you still always want the lowest level control if it's going to be played by a million kids. But we do like the convenience of these things for some of the high-level sculpting. OK, so in this next one, I'll just tell you what happens as it goes. Yeah, so we're going to put in a partial order on the things. The red thing says your current thing actually violates those constraints you told me about, so you can say, hey, fix it for me. And it's like, oh, that's pretty good. And then that particular plan, we run our level generator to flesh out levels that, even if they might be ugly, they don't have symmetry, balance, whatever, they at least have whatever design trick it is to require that concept. Then if you want to change the spacing or rearrange it or rotate it or whatever, you can do that. And then the tool, in the next video, you'll see someone go in and make from the sort of drill down into a particular level, we're going to change this 2-splitter into a 3-splitter, which leaves a laser unused out on the side. This is this concept of wasted lasers. Maybe we didn't mean to introduce wasted lasers just yet. We want to delay that further in the game. So the tool, after our manual edit, will show a little pop-up thing here in a second. That's about its response time. Say like, oh, we did exhaustive playtesting here. There's actually a way to, there's no way to solve this level without wasting a laser. And you're like, well, that actually was what I wanted, even though it violated my thing. Lock that in and fix the rest of the stuff that I haven't locked in yet to do that. So it's not like you're a slave to your own constraints. You can ask for conflicting things. You could say, I wanted this high-level thing, but no, I definitely want that concrete thing. Somehow negotiate between the requirements I have. So this project definitely had the flavor of the requirements in the design process are shifting from minute to minute as we drag and do other stuff. So putting these all together to go from the partial order and these sort of pacing constraints to these, this is a constrained optimization task, which was, I don't know, a 50-line AnswerSet program that we wrote in an afternoon. Not at all anything really difficult. And then to go from a particular column of one of these to a concrete level, that's using our pre-existing space of levels and solutions under certain constraints, particularly under the constraints that these must be required concepts. After you make any manual changes, we then lock down the puzzle and say, is there a way to solve it that avoids any of these things? Rather, if not, then it is required. And then that's how we update the display. And then based on how the display is updated, it's just some evaluating the distance from a spline and so on to check whether there's no real intelligence going that direction. But the important thing is that if you move a single piece down here, it can tell you that single piece caused a high-level change somewhere else and alert you to that within a few seconds. So we did deliver on this mixed initiative design idea. And importantly, we didn't think of actually building this tool until we had all the building blocks sitting around. Like when we made that tool, we spent no time writing combinatorial search code. We spent all of our time implementing sliders and tabbed UI panes and stuff like that. And it was surprisingly difficult to make a nice responsive system that communicated to a solver on the back end. But we would never have put in that investment unless we knew that the things that from a computer science perspective are the hard parts, like UI programming is not hard from a complexity perspective. It should be the search that's the hard part. Turns out UI programming is hard. But yeah, until we had these building blocks around, we didn't think to make the high-level tool. So what I like to do is show these sort of proofs of concepts of what sounds like the hard parts so that people trust those enough to actually do what is really the hard part. And I've been showing all these examples in refraction. We've also applied this to refraction 2 and the game that came after it, which have slightly different rules for how fractions work. You can now rotate pieces and other weird things. We applied it to this another educational game, this one focused on algebra, called Dragon Box. And one of the fun things about Dragon Box is that the state space of the game is infinite in the sense that if you want to, you can just bring new cards out from the bottom of the deck and sort of create new things on the fly. It's not like just spatial arrangement of existing pieces. So we had to come up with a sort of a symbolic garbage collector that reasoned about like all possible ways to play it, assuming that you can always make new cards, but that you probably never need to use more than 20 and so on. We've applied this to word problems where there's an interesting mixture of math and natural language constraints at the same time, and plugged it into a prototype game that it has a new name now instead of Algebra Adventure. I forgot the name. But the dream with that one is that we would write down constraints both on the math involved in the problems, the language used to describe in the sentences the problems, like saying twice versus double or times 2 or something like that, but also have story constraints like this character better do something evil in scene 3 while you are also solving for something that has an intermediate negative result or something like that. And we're not there yet, but we have a lot of the prototypes of the interesting parts. It turns out, of course, there's lots of UI programming involved in being able to drag symbols out of the text and put them together. And so it's interesting change of scope in that. Yeah, so that's the end of sort of the concrete projects. To tell you a little bit about the external impact, because I know, let's see. Well, just at a couple different universities, there are now graduate level classes on content generation that include the design space modeling sort of paradigm and basic introductions to AnswerSet programming as their core curriculum. Students coming from those classes are getting hired at places like Microsoft, more Microsoft Studios than MSR. We have a textbook chapter coming up, which will sort of solidify the inclusion of this is just how you automate design now, even though this is relatively fresh stuff. And there are student research papers coming out, and I should update this to there are now students who have gone past their thesis proposal, like they're continuing this as their primary research. So that feels really good, even though this stuff is new. So a tiny bit of information about future directions. Of course, I'm interested in having better tools and training. Currently, if you want to teach yourself AnswerSet programming, you find these books like written by logicians for logicians, and the practical parts of them assume you're going to be a very logic-oriented AI researcher and so on. And like, I can't just hand these books used in grad AI classes off to somebody, say, working at Microsoft Studios. Like, they just are missing the background, and I don't even want them to learn it through that route. So I want to make a different sort of on-ramp into these technologies, making sure that they are also accessible. There are concrete examples related to design and so on. I'm going to continue direct collaboration with designers and researchers to make either games that couldn't have existed without this or tools that couldn't have existed without this, and have videos of them so people can see like, oh, the refraction design team had that cool tool. Can we have that for our thing? Until they had seen that it exists, they probably couldn't even know what to ask for or what to try to get permission from the rest of their team. And another dimension, the one I'm going to say a little bit more about, is probabilistic modeling. Because so far I've said that artifacts either are or are not in the design space. Really, we might want to have to soften that, and we don't want to just go back to the idea of like there's some generic utility metric, because that's a little bit too generic, doesn't tell us anything about design. So I think attaching the probabilistic story is useful. One thing you can do here is model statistical elements of style. Lots of people doing music generation stuff have, you train a model on, say, a Markov model on the chord transitions used in Bach chorales or something like that, and then sample from that distribution. So there's lots of uses of statistics in generative modeling for more aesthetic stuff. And I like to do that so that we could do that for transfer the style of our handmade refraction levels or other games. Another thing we'd like to do is write constraints about uncertain outcomes. The main use for this would be in player modeling. If you, it's not that players will eventually construct all possible solutions. They will tend to do the more obvious things first. Or you can say, with 80% probability, they'll keep continuing what they're doing. With 20% probability, they'll pick up the piece and try a different thing. If we can write down a model at that perspective, then we can then have not just a constraint program that represents the set of solutions. We can have a distribution of our solutions and say, well, this level has a shortcut, but what is the chance that someone will actually do it? And it'll be like, if it's astronomically small, oh, whatever, it might as well be 0. Or we can have something that's solvable in 2 ways, but we want to make sure that the advanced way is less likely. It's much more likely to be found by people who actually know the concept. So this is, eventually we get back to things like difficulty or inferring whether people know things, but only after we've gone through probabilistic modeling. The last thing would be that being able to give positive and negative examples, and from that, sort of inferring some of these conditions of appropriateness, instead of saying, I'm going to write down in formal logic what makes a puzzle appropriate. I know how to write down the rules of a game to say what is valid or not, but I don't know how to make some of the style things felt hokey when we would write the symmetry constraints and so on. So doing that from data instead of just our own guess would be useful. And then this other side is, what was I going to say about this? Oh, right. In the same way that I separated the definition of the space of artifacts from the algorithms that search it, I would love to, the second one, in a machine learning problem, separate the definition of a space of hypotheses, particularly under their likelihood for a given set of data, from the algorithms to search that space of hypotheses. This is the same setup used in support vector machines, where you just sort of write down your machine learning problem as a constraint problem, hand it off to a quadratic programming engine, and it gives you the optimal answer. Let's see. And I think this could also change the way that you teach people about machine learning if you never get into, or if you heavily downplay the particular algorithms used and just talk about what makes one hypothesis more likely than another on data and so on. And that could potentially make a lot of machine learning ideas more accessible to people who aren't already thinking about algorithms. So some brief takeaways here. Inside of every design problem is a search task. It's not the essence of the problem, it's often the tedious part. That task ranges from hard to insanely hard from a computationally complexity perspective, but nonetheless, you can still solve these very quickly because they are always, at least for games, at a human scale. And despite this complexity, we should mechanize design because of what it gives us in extended creative reach to see and ask for new tools, to see and ask for new games. And the big idea here is that by modeling the space of artifacts, what I'm calling the design space, instead of inventing algorithms, you get new design automation tools, what feels like for free, just by writing down what you want. So, thanks. Any questions? Yeah.
So, I haven't fully thought through this question yet, but all of the games that you've showed have like deterministic dynamics, I might say. So, like,
yeah.
So in applying the approach to a game that says may have like real-time dynamics, like maybe you have to account for like real-time physics or like players involved. How would you necessarily need to sort of reconceptualize the design space?
I think it's all a matter of representation. Like, I'm not particularly married to AnswerSet programming as a representation. That works for discrete deterministic systems really well. But the sort of the opposites of that are stochastic systems, where there's definitely probability, like in any of these RPGs, where there's like you roll a dice to figure out how much damage you get, or in a say a racing game where it's all about position and momentum and skid, and it's all vectors and continuous spaces, you would use a different constraint solving backend. But I think the same idea of modeling the space of what's appropriate, or locking down the design and modeling all the ways the player could interact with it under some abstraction or whatever. You don't. I have a new project coming up where I'm analyzing the actual native binaries of things, but I'm not going to say I'm going to apply that to like some giant racing game or something like that. You would always apply it to the abstraction that is relevant to the type of design thing you want to do. But yeah, stochastic and continuous are areas that I've not represented at all yet, but I think with a change in the constraint solving technology still fit.
And is there possibly, when you get to the level of trying to do the third step, like the human mixed initiative thing, or maybe some of those spaces harder to abstract than others?
Well, I think some of the ones, like when I showed the progression plan of like which concepts are involved in which level, like that transfers to many other games, like with zero changes at all, because progressions themselves are these discrete, I mean, you could have branching story things that are not like a stripe, but they're more interesting graph structure. Where it gets tricky is we had this pre-existing level editor for refraction levels that actually took like 6 months to make. It was this horrendously complex thing. And we just sort of embedded that in our larger tool. That you need to have the sort of manual authoring tools in place, plus an engine that can do simulation for the game. And if you have those things, you can bundle them together to make the rest of your design tools. And that's a lot to make, particularly for new genres. So I'm hoping that as I get in contact with, say, people, the vendors for game engines, working with them so that there's sort of like the real game engine you deploy your game with, and then there's sort of a symbolic replacement that you use during analysis that abstracts out the physics. I mean, that's a big thing to do, abstract out the physics. There are things you can do. You can say there are logical time stacks, things move along straight lines or move along analytic parabolas and so on for a platformer. There's tons of work in symbolic computation that is just like game development people just don't even know exists. So I'm sure there's tons of low-hanging fruit in terms of possibilities to combine those.
So have you thought of educational games for teaching programming?
Yeah. Well, so I was heavily influenced by that Lost Mind of Dr. Brain game, and I played a lot of Minecraft and so on, and I've actually made circuits in it. I think, one of the things was that when we were playing with different variations of refraction, we realized that refraction is sort of only about fractions on the surface, on like the labels that say 1/2 and 1. It's really like a data flow programming exercise embedded in a space. So like the splitter node doesn't have to split things equally. It's just a function that has one input and two outputs that don't even necessarily be the same. So you could map other types of computation into exactly that same shell of a game, but I think other things where people are building a state machine, watching it execute, and then there is, if I go back to,
Where are the loops there? There's no notion of looping there, right?
There are plenty of games where there are, I can find those things at the beginning. There might have been a faster way to get back. So in a game like Space Chem, you are building basically multi-threaded looping programs that communicate. Like this is just one view and inside of one building on a larger map, and each one of those has multiple looping tracks. This little bracket shape here is sort of like a program counter that goes by doing those instructions. So there are definitely games that are played not by people to learn to program, but they're just as an interesting puzzle game that like involve like very deep programmer type reasoning, as well as debugging. And one of these tools down here is essentially a breakpoint, and I don't remember where that button is, but you can set it, and if the program counter ever gets there, it pauses it, you get to inspect things and continue.
Who developed this game?
A company called Zachatronics, I believe they are somewhere in the Northwest, if not like somewhere in Seattle. I mean, it's an indie game. It's not as, I'm sure it's sold 1 million copies, not 100 million or something like that. And most people don't play it all the way through. But this is another game that has fixed levels that were designed by the small team that made the game. They do allow the community to make new puzzles, and those people uncover new design possibilities and so on. But nobody's working with any sort of assistance. When they make the puzzle, they can't even. It would be nice if they could say, when I make a puzzle, at least show me one reference solution, and then I will try to make features of that required or forbidden and so on. Whereas people might spend an hour sort of debugging their puzzle in development before they upload it. And I don't think you would necessarily use this in an early programming curriculum, but it's definitely, but there are games that people are already making that have these, or like I showed these ones before. In Manufactoria, you build this thing that basically sorts robots based on the contents of their internal tape. And it basically does sort of a randomized testing. Like if your little contraption with conveyor belts and switches passes, I think, 10 or 100 test samples, then it's considered a valid solution. So like the really aggressive way of playing this game is making solutions that are incorrect, but will pass the test with a certain likelihood. Really, it should be doing something like giving you the test that it knows will break your thing. Or it should be doing that with some probability or something like that. But the people who made this, they're just Flash game developers who don't have knowledge or access to the same type of automated testing you would have for more heavyweight things. And I think those people just need to know these things exist, and they need to have them cross-compiled so they can be used in Flash. That's another thing, is like a lot of these cool formal methods tools assume, like, are not meant to run in the Flash VM or whatever. So I got an AnswerSet solver to run in a browser only by cross-compiling it into JavaScript. So I've got this like 5 megabyte JavaScript file, which is the solver, and it runs 50 times slower than native but it works. And for small demos, maybe that's fine. Or for small games, maybe that's fine. But that's like a requirement that doesn't normally come up when you're not deploying things to restricted environments.
Any other questions? We have one last question.
Yeah.
So can you comment a little bit more on the scalability of ASP?
So there's sort of two. At first, when I was thinking of, if I can find one of my pictures of, people would often ask, like when I showed them like the 10 by 10 levels of refraction with 16 pieces and however many other non-movable pieces, the questions were like, well, how does it scale to larger things? And from the first kind of scaling to large problems is one that, because of the human context, doesn't actually come up. The kind of scaling that's actually more interesting is like how else, or sorry, before I go into that, there were certain representation tricks that we learned in this one. Like instead of representing the position of a piece like with a predicate that says it is true that this piece had x coordinate 6, we represent that 6 by its binary representation. And as a result of that change in representation, now we can handle tremendously large grids. We can say, oh, for only adding 32 billion variables to it, we can now represent 2 to the 32 possible positions. Which, I mean, we could have also gotten that benefit from switching to a numerical constraint solver instead of a Boolean constraint solver. So there are certain spatial dimensions of scalability that with the right representation totally go away. We would never care about a problem where there are like 10,000 puzzle pieces, because no human is going to play a puzzle that they have to, first of all, just move each piece 10,000, do a minimum of 10,000 pieces just to move them, even if they knew the right solution right away. So that dimension of scalability isn't one that we ever care to tackle. The harder one is, how do you get people who have just taught themselves this stuff last 6 months to get them to write efficient and compact logical encodings? Because that's something I know how to do 6, 8 years into this, but that knowledge is not written in any useful book, because all the books are about theorem proving in the abstract, not like writing compact and efficient things. So maybe in the future, languages that are more domain specific, that don't make it so easy to shoot yourself in the foot, would be a response to that. But usually the thing that saves you is that if it's attached to a human consumption context, you never have to like scale to infinity. N is always finite. It might be 10, it might be 100 or whatever, but it's fixed.
Thanks.
Yeah, thank you.